Today the dynamic programming will be discussed. How dynamic programming technique is used for solving the nonlinear programming problem, that part I will discuss today. Now, in dynamic programming problem there are few properties. First of all, the dynamic programming can be also named as the multi-stage programming problem, because whenever we are dealing with a big problem, it is we have to take decisions sequentially at different points in time, in different points in space, and even we can divide the whole system into different subsystems and we take decision for individual subsystem, and from there we are finding out the optimal solution for the whole system, but all the decisions are taken in sequence. First we consider the first subsystem, second, third, in this way we are proceeding. That is why, since we are considering different stages, that is why this dynamic programming can also be named as the multi-stage programming technique. Now, if we have invariable nonlinear programming problem, then a set of nonlinear programming problem can be solved, can be defined as a multi-stage nonlinear programming problem, and the multi-stage nonlinear programming can be solved sequentially by solving different stages separately. Now, that part today I am going to discuss which kind of nonlinear programming problem can be solved using dynamic programming technique. Now, there are certain basic principles of dynamic programming technique, that part I am discussing today. First of all, the first part is that the whole system has to be decomposed into different stages. For decomposition of the system into different subsystems, person should have the skill of doing that, then only a n dimensional problem can be defined in one dimensional problems. That part you need to understand. Now, it has been invented by Richard Bellman in 1950, and here dynamic means we are considering the situation in different time scale, different space, different subsystem, different platforms. That is why this is dynamic in nature, and programming we are using in optimization for planning, and that is why this kind of situation where a problem can be decomposed into different subsystems can be tackled using multi-stage decision making problem, multi-stage programming problem, or dynamic programming problem. Now, the entire dynamic programming problem is being dependent on the Bellman optimality principle. That is why we need to know what is the Bellman optimality principle. Now, one thing is that whenever we are considering a nonlinear programming problem, we are considering the objective function as well as the constraints are continuous in nature and continuously differentiable. If it is not differentiable, our classical optimization technique is not applicable there. That is why here also that necessity is there. For solving the problem for the nonlinear programming problem, we need to have the function as continuous and differentiable. Now, we will solve in the next. Now, how to define, how to decompose the problem? There are few parts of it. First of all, we have to define the problem into different stages. Now, each stage will have different number of steps, and we will have one transformation equation in individual stage, and this transformation equation will be we will iterate in different stages to get the optimal solution at different stages, and the optimal solutions of the different stages, these are connected very much sequentially, so that whatever optimal solution we will get finally at the final stage, that will be optimal solution of the original problem. Original problem is the problem which is big in nature, which is very large. We are decomposing it into different subsystems. That is why for every problem our task is to first define the stage, then we have to define the states of individual stages, and we have to define the transformation equation, transformation strategy in individual stage, and how transformation equation is taking role of changing the stages. That part I am going to discuss today. Now, if I just explain it graphically, then we will say that each stage, that one stage transformation equation will be there. This stage transformation equation will be responsible to convert the state Sn minus 1 to the resulting state Sn. And what are the inputs for it? The input will be the decision of the previous stage, and for each previous stage we will calculate the immediate return, and we will use the state transformation equation to reach to the final state. This is the basic idea. How it is being used, I will explain you in the next. But the whole dynamic programming problem is based on the Bellman's principle of optimality. Bellman's principle of optimality says that an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. That is the beauty of the optimality principle of dynamic programming, and how this optimality principle is being maintained throughout the whole stage. That part I am going to explain. Now, there are certain variables, certain symbols we are using in dynamic programming problem. Those let me summarize first. Now, stages are being named as n. When n is equal to 1, we are at the first stage, but that is also the convention that the initial state is being numbered as n is equal to 0. Now, for individual stage we will have the state variables, that is Sn, and from individual stage we will have the optimal decision, that is the Dn. This optimal decision will give the return to the next stage. Rather, this optimal decision will produce the return which will be considered in the state transformation equation. That is, the return is being termed as Rn Dn. Dn is, if it is the decision variable of the nth stage, then we can say Rn Dn would be the corresponding return for that decision. We can have different values of Dn at individual stage. Corresponding to Dn, we will have different Rn Dn, and by using the transformation equation, we will reach to the next stage from n to n plus 1, Sn to Sn plus 1, all right. And the function f is the optimal function will be calculated. Now, for that thing, let me consider one nonlinear programming problem where we are having one additive constraint and we have the objective function that is in the form of multiplicative separable return. Okay. This model we are considering for explaining the situation how really we are using the dynamic programming for nonlinear programming problem. Now, let me consider the model as we have to find out the maximum of f1 x1 f2 x2 up to fn xn. That means we are having multiplicative separable return. As I was mentioning before, that a separable function is being considered here, you see, because the objective function can be expressed as different separable functions, which the separable functions are the functions of individual decision variables. If it is of this form, then we can use the dynamic programming to solve the problem. Now, this kind of problem can be solved with other techniques as well, as I have discussed before, the constraint optimization techniques. But this dynamic programming very nicely can solve, very effectively can be solved, and very easily we will get the optimal solution of it. You see, we have considered the objective function as the multiplication of different functions of individual decision variables. Instead of that, we can have the objective function as the additive nature, where we will have the functions of individual functions which are additive. That means we will have the functions in the form of summation in place of product. Alright, we are considering the simple model here, and the constraint is of the form single additive constraint. We are having only one constraint. This is the simplest model we are considering. Now you see how really we are defining the stage, how really we are defining the states for this problem. Here A1, A2, An, these are all the constants, B is another constant, and Ai's can be positive, Ai's can be negative as well, same as for B, but x1, x2, xn, these are the decision variables. Alright, this is the model for us. We are going to apply the dynamic programming technique, rather the Bellman's principle of optimality, for solving this kind of problem. Now, first of all, we have to define this problem into different stages. Alright, let this problem is considered as n stage problem, where suffix I indicates the stage. That is why we need to decide the value for xi, and for each value for xi we are having I is equal to 1 to n, we have to introduce the state variables for individual stages. That is why you see, whenever we are considering at the nth stage as the combination of n variables, n minus 1th stage as combination of n minus first n minus 1 variables. Second stage will be considered as the combination of some additive combination of the first two variables a1 x1 plus a2 x2. Thus, the first stage variable will be considered s1 as a1 x1. If we considered the state variables like this, you see, we can say S1 would be is equal to a1 x1 plus a2 x2. That is why this can be written as S2 minus a2 x2. That is, you will get a pattern, you see, Sn minus 1 would be Sn minus an by xn minus xn. In this way, we will have a pattern to it, and next we are going to formulate the recursive formula. Now, dynamic programming problem, as I said, we are having the state transformation equation at individual stages, and this state transformation equation will play the same calculation, will have the same calculation in each iteration. That is why this process is a recursion process, and we are going to define in the next how the recursive formula can be defined from here. You see, if we define the problem from the constraint set in this way, if we redefine the variables instead of x1, x2, xn, if we just redefine as s1, s2, sn, okay, we are just transforming the variables from the set of x1, x2, xn to s1, s2, sn. You see, we are getting a kind of recursion there. There is a recursion process. Always Sn minus 1 would be Sn minus xn, an xn. That is why I put xn is equal to 1, you will get one set, n equal to 2, you will get another set. In this way, you will get the this way. Now, you see, we are having the recursion formula like this. Here, the objective function is of multiplicative form, alright. That is why at the nth stage, if we define it this way, fn xn is equal to maximum of small fn xn, that is the function with the nth value only, and this is the capital F n minus 1 s n minus 1, this is the optimal value for n minus 1th stage. That is why you see the Bellman's optimality principle says us that we did not to think about the initial condition, we are only concerned about whenever we are in one stage, we are concerned about the previous stage. That is why at the nth stage, we are considering as input the optimal value of the n minus 1th stage and the objective function of the nth stage, nothing else. Since the problem is of maximization type and this is the multiplicative in nature, that is why I can say return at the nth stage is equal to, we have to maximize fn xn fn minus 1 sn minus 1. See the recursion here, you start from n is equal to, we can go in dynamic programming, there are two ways we can do the recursion. We can go forward recursive formula we can use, we can go from 1 to n, we can do the backward recursive formula as well, from n to 1 we can do. Okay. Here we are going from 1 to n, if we know 1 we can calculate 2, if we know 2 we can calculate 3, in this way we are proceeding. Once we are calculating for n, we need to know for n minus 1, okay, that is the case. Now we will solve one nonlinear programming problem with this recursive process, okay. And we will first calculate f1 s1, then f2 s2, then f3 s3, and we will reach to fn sn. And every optimization problem would be problem of single variable, because you see here only the variable is xn, no other variable is involved here, all right. All other variables are not changing, only xn is changing. For different value of xn, which xn gives you the maximum return, that would be the optimal at the nth stage. I hope you understood the basic principle of dynamic programming. Let us apply this problem for the one specific nonlinear programming problem. Now, what is the procedure for doing the for applying the dynamic programming technique in nonlinear programming problem? First of all, we have to define the problem variables, we have to determine the objective function, we have to specify the constraint. Then we have to define the stage, determine the state variables and corresponding decision at each stage we need to find out. This is the steps we need to follow one by one. Once we got it, after that we have to specify the relationship state of one stage as a function of state and the decision of the next stage if we go forward, all right. Now, after that, after doing this, we will proceed, we will follow either the forward recursive formula or backward recursive formula to get the optimal solution at different stages. These are all connected with each other. One optimal solution will be of one stage would be the input of the next stage. That way we will proceed. It could be forward recursion, it could be backward recursion. We will use it and we will solve the problem after that. Okay. Now, let us consider a problem. Maximization of x1, x2, x3 subject to x1 plus x2 plus x3 is equal to 5. You see here the objective function is of multiplicative, return and constraint is of additive type. Now, we have to use 3 state variables like this. By considering S1 is equal to x1, S2 is equal to x1 plus x2, S3 is equal to x1 plus x2 plus x3. We are just transforming from x1, x2, x3 decision variable stages we are to S1, S2, S3 combinations. Okay. You see we are getting a pattern, S1 is equal to S2 minus x2, S2 is equal to S3 minus x3 in this way. Okay. Clear? Now, if this is so, you see the first problem, the first stage problem will be only we are having the objective function is x1, x2, x3. With the first state variable, we can formulate the subsystem as maximization of x1. Maximization of x1, there is no constraint, there is no end of it. That is why no optimization can be done at this stage. Let me proceed to the next stage. We are going forward. That is the next stage is f2 s2. Okay. This function, how the function is? The function is maximization over x2 into x2 and f1 s1. alright, the previous. Now, you see f1 s1 is equal to x1, that can also be written as s2 minus x2. That is why this problem can be defined as maximization of x2 into s2 minus x2. Then this is a unconstrained problem of one variable, that is x2, and we will get the first necessary condition for it. If we just take the first derivative with respect to x2 equate to 0, then we will get x2 is equal to s2 by 2. Alright, we can go for the second order derivative as well to get whether this is gives you the maximum value or not. That also we can do with this value. Alright, this is quite clear that your function is x2 into s2 minus x2. That is why if I just differentiate twice, we will get the value as minus 1. Minus 1 means this gives you the maximum value. That is why you see the optimum value we are getting x2 as s2 by 2. Okay? Let us move to the next stage, that is the stage as x3 rather s3. If I just write down f3 s3, this is equal to max of over x3 only, x3 f2 s2. Just now we got f2 s2 is equal to what? f2 s2 is equal to x2 into s1. Alright, is it clear? x2 into s1 we got, and what is the value for x2? x2 value we got as s2 by 2. Okay, x1 can be written again as s2 minus x2. That is why x1 is s2 minus s2 by 2. That is why that is also s2 by 2. Clear? That is why the optimum value up to the second stage we are getting s2 square by 4. Alright. And we are having the function as maximization x3 s2 square by 4 this, and maximization of x3. This is again one single dimensional problem where no constraint is there. x3 is the free variable, it can take any positive value from 0 to infinity. Now, again we cannot do with s2. We know the relation that s2 is equal to x3 by x3. That is why let us convert it into that form, we will get it. And from here, by using the differential calculus method, we will get x3 is equal to x3 by 3. What is your s3? s3 is equal to x1 plus x2 plus x3, and you have the constraint that x1 plus x2 plus x3 is equal to 5. That is why you are getting the value for x3 is equal to 5 by 3. Once you are getting the value for x3, you will get the value for which one? S2. How we will get the value for S2? S2 is equal to x3 minus x3. You will get the value for x2. You will get the value for x1 as well. That is why we can, you see, we can solve the problem very easily like this. We will get x1 is equal to 5 by 3, x2 equal to 5 by 3, x3 equal to 5 by 3, and the objective functional value would be 125 divided by 9. Clear? Now, we applied the Bellman's optimality principle for the case where we were having the multiplicative objective function additive constraint. We can have the other way as well, additive constraint additive separable return, that is another model. You see how really we are using the state transformation equation, how really we are using the recursion formula here, just you see. First of all, for this kind of problem, we have to define the state variables. How many stages we can define for this problem? We can have n number of stages. Similarly, let us use the similar kind of state variables, because constraints are of similar kind. Generally, whenever we are using the nonlinear, we are going to solve the nonlinear programming problem using dynamic programming technique, we are forming the state variables from the constraint set only. Looking at the constraint set, we have to decide what kind of state variable we will use, because constraint set will give you certain values. That is the only the restrictions we are getting in terms of numerals. Okay? That is why from there only we have to do it. Now, in the similar manner we will proceed. Let me take one example for this. Just to see, we are having the problem minimization of x1 square plus x2 square plus x3 square. Now, you see the objective function is of type f1 x1 plus f2 x2 plus f3 x3 subject to a1 x1 plus a2 x2 plus a3 x3 greater than equal to 15. All right. Now, you see summation of these three is coming as 15. Can you guess what could be the minimum value of x1 square plus x2 square plus x3 square? Try to guess it. Okay. Now, let me solve it. Let me consider three state variables just like the previous one. S1 equal to x1, S2 is equal to x1 plus x2, S3 is equal to x1 plus x2 plus x3, and we know the fact that S3 is greater than equal to 15. We know that fact and we have these relations as well. Let us formulate the transformation equation. Let me go from the first stage, f1 s1 x1 square, f2 s2 minimum of over x2, x2 square plus f1 s1. Let me convert x1 as s2 minus x2, that is why minimization will be done this way. Similarly for 3, if we just use the differential calculus method again, we are getting x2 is equal to s2 by 2. You can check it whether this is correct or not correct, and the corresponding functional value we are getting s2 square by 4, because this is x2 square, it is not 2, it is 4. Okay. Clear? Now, we are moving to the third stage. Now, we know this fact, all right, this is 4, we know this fact. If we know this fact, we are getting x3 is equal to s3 by 3, all right. What is the minimum value for S3? Minimum value for x3 is equal to 15, we know. From there, we can get that f3, s3 minimum of this, certainly s3 is equal to 15 will be the minimum value, all right. If s3 is 15, then we will get s2 is equal to, and for which value of x3, that is x3 is equal to s3 by 3, that is why x3 would be is equal to 5. If you get x3 equal to 5, then you will get x1 plus x2 is equal to this 10 and x2 is equal to 5, x1 equal to 5. That is the minimum you must have guessed before. Okay. This way we can solve the problem. Let me consider another model. You see, we are having the additive return but multiplicative constraint. Then what kind of state variable we will consider in this case? We will just, as I said to you, that looking at the constraint set, we have to decide about the nature of the state variables. That is why the state variables would be, Sn would be the multiplication of this, Sn minus 1 would be this, and S2 would be this, S1 would be this one. Only the changes are there, you see the pattern is changing, instead of minus, here division, because the constraint is of multiplicative type. All right. Let us solve the problem again like this. Okay. Let me use the state variables. Let me solve. We will get the solution. We will see that x1 will be is equal to this, then x2 would be is equal to this one. If we just use the the differential calculus approach over x2, then we can get the value of x2 is equal to 15 root of 15. Okay. Now, if x2 is root of 15, then x1 would be again root of 15. Then we will get the value for x3 as well, but we need to proceed for the third iteration, otherwise we cannot complete the process. That is why we are moving to the next iteration, that is S3. All right, S3 is this one. Again use the differential calculus approach and we will get the value for x3 is equal to 15 to the power 1 by 3. Okay. Now, we are getting the objective functional value, you see 3 into 15 to the power 1 by 3 from here, all right. And what about what about the value for x 2? Value for x 2 was 15 to the power 1 by 2, all right, and x 1 is 15 to the power. Just to check whether we are getting the same, satisfy the same constraint or not. The multiplication is coming as, how much is coming?
Root 15 into root 15, 15, so other one should be 1.
That is why individually it would be 1 by 3.
It would be 1. X3 should be 1.
X3 should be 1.
Huh?
X3 should be 1.
X should, you just do the calculation once more. I will give you more assignments on this part, and we will give you the solution as well for this problem. Now, try to solve this problem using the end stage dynamic programming technique. Thank you for today.